Today, before starting to present, I'll be thanking everyone for giving me this opportunity to present here. Today, I'll be talking on the analysis of H1 centimeter images to probe the epoch of reionization using largest cluster cells. This is a brief overview of what I'm going to cover today. Now, as the eminent speakers before me have already convinced, why is it important to study the cosmic dawn and the epoch of reionization? So I'll skip this part. And to summarize the potential challenges in detecting the 21 centimeter signal, let's say that the main challenges are the foregrounds, and additionally, we have different telescope effects, the beam effect, and effect of ionosphere that creates additional challenges in detecting the 21 centimeter signal. Now, what you see here, what you see here on the left is a fiducial model simulation that has been done, and on the right, it is the corresponding halo density field that talks about the sources. And now, talking about the motivation of this work, what we want to do is, in principle, if we get an image like on the left panel, if you get an image on something in the left panel, we would in principle be able to find the corresponding thing on the right panel. So if we can get maps like this, we would be in principle be able to tell about the sources and the different IGN properties. For example, we can tell about the mass distribution spectra of the sources, and additionally, we can talk about the physics of the intergalactic medium, which involve Lyman alpha coupling and X-ray heating, etc. So in principle, we would be able to track the entire reionization history if we get an image something like that. So the first generation telescopes, what they try to do is that they try to do interferometric studies, and because they don't have very high sensitivity, they use this different Fourier statistics method to analyze the signal. Now there are methods that can be applied directly to the image on the image plane, and Barg et al. 2019 focuses on the first two methods where he tracks the largest ionized region to find to tell about the shapes and the connectivity of these ionized regions using these two methods. So Pathak et al. 2022, where I am a co-author, we have been following the same work, and we have been trying to investigate whether these methods can differentiate between different source models and subsequent reionization scenarios or not. Now, to simulate the reionization environment, we use a semi-numerical technique, and where these are the different details of our simulation. And we use a particle mesh n-body simulation followed by a friends of friend Hello Finder to finally create our reionization maps. And we create these maps for using different source models. So these are the different source models. In general, they are distinguished by two parameters. One is how the number of photons is related to the host halo mass, and secondly, how the rest frame energy distribution is there. With the different four source models you saw in the last slide, we create 6 different reionization scenarios where what we have done here is that we tweak this parameter n ion in such a way that the history remains same for each model, and we can actually have comparison for the comparison has to be there for every model in the same state of reionization. Now, this is a representation of how the different reionization scenarios looks for a particular redshift or a particular neutral fraction. And the question that we want to answer here is that can we distinguish these different reionization scenarios using our technique? Now, in order to understand that, what we have to understand is what is the percolation transition. The percolation transition is the time where we find that different small ionized regions coalesce together to form a large singly connected ionized region. And we use the technique of LCS to, or the largest cluster statistics, to get insights on this particular percolation process. Now, LCS in general is the ratio of the largest ionized region to all the ionized regions. Now, in our particular case, we are considering a simulated volume. So LCS would be the volume of the largest ionized region, the total volume of all ionized regions. Now, to complement this analysis of LCS, what we use is the shape finders, and which are calculated using these Minkowski functionals. And using these Minkowski functionals, we employ a tool called SurfGen2 to find the morphology of the individual regions that are quantified with these two quantities called planarity and filamentary. And finally, we want to answer the question whether we can track this percolation process using this LCS method and this shape finder method. So what you can see here is that we can actually distinguish between different reionization scenarios using this LCS. What we see is that there is an abrupt phase transition in the LCS where different small ionized regions coalesce together to form a big ionized region. And this transition point is termed as the percolation threshold or the percolation transition point, which is shown in the dotted vertical lines here. Now, similarly, as you can see, this quantity thickness cross breadth is called the effective cross section, where we see that the effective cross section for these individual regions, they remain almost same, but in case of the length, the length actually is magnitudes of order, like orders of magnitude higher than what we see the change in thickness cross breadth. And this is a summary of what we had found in that, and we see that ultimately it leads to a filamentary nature where all the shapes they get interconnected, and they tend to have a filamentary structure. Now, what we'll essentially get from an interferometer is that we would not get the 0th K mode, where we would not get the mean of the particular signal. So what we did was we tried to analyze the mean subtracted fields, and this is the visual representation of those. And now, as the mean has been subtracted from these maps, it is important to take account of the threshold. And thorough analysis of the threshold actually led us to believe that if we have to take varying threshold instead of taking a constant threshold. And with choosing a proper threshold for this case, what we see is that we have, for this particular case, we have chosen the threshold to be the minimum of our particular field. And what we have seen is that the mean subtracted case actually follows what the non-mean subtracted case was. And then what we wanted to do is that we wanted to force in our simulation to grid spacing of 2.38 cubic megaparsec. And there also you see that the results are consistent with what we have found earlier. Similarly, the shape finder results are also consistent with our earlier findings. Next, we wanted to go to a more realistic scenario where we employed a Gaussian noise of RMS 3.10 millikelvin, and alongside we also smoothed the data with different length scales of Gaussian kernel. And now, as we add noise to the data and smooth them out, what we see is that the choice of threshold becomes even more complicated, and a proper threshold has to be chosen. So for this particular case, we employed the method of gradient descent. So in a typical histogram for a 21 centimeter map, we see that it's of a bimodal nature. So one of the peaks represent the ionized pixels, and the other peak represent the neutral pixels. So with this gradient descent method, we try to find the local minima here, which we chose as a threshold, because our SurfGen2 code actually wants a binarized field where it applies the Marching Cube 33 algorithm that it works with. And after choosing a proper threshold, now we see the effect of smoothing for a lower smoothing length scale. We see that we still get the features of LCS, but as we move to higher smoothing scales, we see that the features of LCS are lost and they go erratic. Now, when we incorporate just the noise, we see that the LCS still is consistent with our earlier findings. So we would essentially need to move to a higher noise level, which we are doing currently. When we combine the effects of smoothing and noise, what we see is that the percolation transition point shifts heavily. And what you see here is that for higher neutral fraction values, you don't get the values of LCS, because the small ionized regions that were there, they were completely smoothened out. Now, to test the robustness further, what we wanted to do is that we wanted to take our images as a sky model, and we fed it in our pipeline, which mimics the behavior of SK1 low. And this is a simplified schematic of our pipeline. So we use this pipeline to mimic the behavior of SK1 low, and these are the details of our pipeline. And what we had was we had a baseline around 2 kilometers from the central station, and our integration time was 120 seconds, and for an observation time of half an hour. And this was pointed at a direction where the right ascension was 15 hours and the declination was minus 30 degrees. And after we employ this on our maps, what we see is that there are different edge effects that can be visible in these maps. And we suspect that these edge effects come due to the fact that our pipeline particularly employs an FTW scheme, which actually works best for the maps who has a grid size of 2 to the power, in the order of 2 to the power of n. But we had our maps of 300 grid cells. So what we had to do is that we had to go for maps which have a grid size which has the order of 2 to the power of n. Now, along with these artifacts, what we have also observed are different other artifacts that come due to the cleaning algorithm that is being employed on these maps using CASA clean. And because of that, we see that there are wrong inferences of LCS as we had seen in our earlier findings. And when we tried to analyze why it was coming, we saw that the histogram that is typically which had a typical bimodal structure was getting smoothed out, and we lose the features and we couldn't employ our scheme of the threshold that we use gradient descent in our last case. So we have to go for a better thresholding algorithm as well. Now, as I already mentioned that we are working on resimulating these H1 maps, and when we resimulated our H1 maps, we see that the 256 cube grid size maps are also consistent with what we have found with the 300 cube grid size. But now we have to feed these 256 cube maps to our pipeline and have to see if the artifacts still come or not. That work is that work is actually going on right now. And so, as I have mentioned, that we need to search for a better threshold finding algorithm. So for that, we are considering different techniques like superpixel and SegUnit to find a better threshold for our LCS analysis. Alongside, we want to run LCS on these observational maps, and the cleaning algorithm can be improved. And after that, we want to test the higher limit of this LCS analysis for a higher noise level. Also, we want to compare different telescope effects and check the validity of this LCS-like analysis on these observational maps. So that is it for my presentation. Thank you.
A picture of the baseline coverage. And which is the region that you are using? The entire region, is it?
No, we are using this one.
So it is more or less uniform there, or I mean, is it entirely covered, or?
It's almost covered.
So why do you need clean? I mean, suppose you just made a dirty image.
Yeah. So in order to run LCS, what the artifacts that we see there, I haven't put up the picture here. So the artifacts actually, what happens is that when you see the maps, the Surgeon 2 tool that we use here, it actually confuses between the artifacts and low density regions or ionized regions. So that for that actually we need to have a better.
Why are you getting artifacts? I mean,
we suspect that firstly the cleaning is not.
No, why are you cleaning? That is what my question was. Is it essential to clean to make an image?
Okay, so
in
because
this case,
the maps.
Is it necessary to clean this image? That is my question.
Yes, otherwise there are artifacts. If you don't clean the image, there are artifacts that leads to wrong interpretation of the LCS.
I see. But I mean, if you have more or less entire UV coverage, do you have a picture of the dirty beam by any chance? No.
No, not.
But you have seen the dirty beam?
Yes.
What does it look like?
So the central part of the image that actually looks like it's either it's a low density region or it looks like an ionized region.
Okay, thank you.
So the initial image you make, so that has the highest baseline within that circle, is it? Or
yeah.
You make a higher resolution image and then...
No, we take our simulated maps as the sky model and then we run it through the pipeline.
No, that I understand. But when you make the image, which is your cleaning, so that you make at a higher resolution and then reduce the resolution, or
no, it's
you make at the resolution
yes,
of that center
yes.
thing.
A very naive question. When you measure your LCS in simulation box, do you assume it's a periodic boundary? If
Yes,
it can
yes.
happen that the ionized region is very close to the corner of the box,
Yes, yes,
and then it goes.
yes.
And the other thing is the LCS. How do you characterize the LCS when there is a significant overlap? I mean, a huge overlap.
Okay, so the definition of LCS, as you can see here, is basically the volume of the largest ionized region. So when there is a big overlap, that means the volume of the largest ionized region is almost equal to the simulation volume. So that is why for lower neutral fractions, you see that the LCS becomes 1, which covers the entire section.
I mean, the largest volume of the ionized regions can still have neutral patches, right? Because the dense regions, like galaxies, will still have neutral fraction. No, because your ionized regions will never be like.
So
I mean, there will be some dense regions like Lyman limit systems or DLAs at those redshifts. I mean, of course, your resolution of the simulation box may not be resolving those scales, but those will still be there.
Yes, yes. We might need to investigate that further. Yes.
Any other questions, comments? Okay, if not, let's thank the speaker again.